Alright, so now let's move on to even and odd functions, which is still 1.2 notes in calculus. Basically, even functions are symmetric about the y-axis. The example is that y equals cosine of x, which I've already taken the liberty and drawn over to the right-hand side. That's that y equals cosine of x. If I was to draw a solid line straight down my y-axis, I could fold along that y-axis and I'd get the same thing on both sides, or at least roughly with my drawing. That is not the most accurate all the time. Other than that, an odd function is symmetrical about the origin. So if I took the point 0, 0, and I flipped it along the x-axis and the y-axis, basically, I would end up at the same spot. So odd functions look the same right side up as they do upside down. The other way to think about symmetrical about the origin is that you can think about the function as symmetrical over the line of y equals x, that very basic algebra 1 line, parent function of all linear functions. Alright, so the technical definition of algebraic properties is that an even function has the property of f of negative x is equal to f of x. So if you plug in a negative x, then we're going to obtain the original function. So all that that's trying to say is if I pick some random distance across and I call it x, alright, so at this point I'm going to get some positive number. So if I choose that same distance over, that negative distance, then I should get the exact same y value for my answer. That's the special thing about even properties versus same thing down here. If I choose a positive x value from here, it's going to end up with the positive x value over here as my y. Versus if I plug in a negative x value, should be the same distance from 0 because they're both x's, then I would probably get the opposite of the original. Meaning down here I would have the negative. It could be flipped to where it's positive over in this section and negative over here. It's just not as common, especially with basic functions, parent functions. Alright, so proving these things algebraically, we need to prove whether or not the following functions are even, odd, or neither. So we're looking at the function of g of x is equal to x cubed minus x. So the first thing I'm going to try to do is I'm going to go ahead and use that f of negative x from both. So I've got g of negative x is going to be equal to negative x cubed minus negative x. Anywhere that I see an x in the original equation, I'm going to plug in that negative x. Alright, so now what I'm going to do is I'm going to simplify this as much as possible. So negative x times negative x times negative x is going to give me a negative x just in general. And then minus a negative is going to give me a plus an x is equal to that g of negative x. Cool, cool. Alright, so that's as simplified as I can get that, especially if I was just to plug in a number, for example, instead of just an x. It would turn out to be just two different numbers, so that's why I'm not simplifying those x's. So now I look and I see, okay, is that the exact same thing? Do I have the original function again that I initially had? No, I don't have x cubed minus x, so that's unfortunate. So the next thing I look for is, did we attain the opposite original of the function? Well, yeah, I've got negative x plus x instead of x cubed minus x. So in this particular case, it would be an odd function. Alright, on B, there is a little background knowledge. There's a reason I reminded you guys that, hey, cosine is even, so that's going to play into this next example. So I've got h of negative x is equal to 1 plus cosine of negative x. Spoiler alert, cosine is even, which means that h of negative x is equal to 1 now plus positive cosine of x. So I did end up with my original function again, which means that this particular equation would be even. Alright, nifty. Next thing that we're going to talk about is those piecewise functions again. I know that they were your favorite from Algebra 2 and pre-calculus. They do build up to calculus concepts, so yes, we have to review them here as well in calculus. So piecewise functions are just some functions that are broken into tiny pieces and behave differently depending on the restricted domain of each piece. Such functions are called piecewise functions. An example of a piecewise function that's pretty nice to start with is that absolute value function, which is that f of x is equal to the absolute value of x. We just need to be sure that we're getting used to this, and we're going to be trying to use the correct domain restrictions. So first thing we got to do is draw this piece of graph, probably, to get a visual. So drawing this absolute value, we should keep in mind that our main points should be 0, 0, 1, 1, 2, 2. It does happen to be reflected across that y-axis, which would make it even, which is pretty nice to help us. So if we notice that this f of absolute value of x technically has two pieces of its domain, and we should be using that appropriate domain for each piece. What I'm talking about when I see two pieces is that I'm seeing, okay, I've got this line sitting over here that I'm going to go ahead and highlight in yellow, as well as I've got this other piece sitting over here that I'm going to go ahead and highlight in green. So now we've got to create this piecewise function, so that way it's actually had a relevant domain all the way across. So the yellow piece that I see is actually going to be, if I can get out of my highlighter, my yellow piece that I see is just going to be that y is equal to negative x. That's it, that's all. And my green line sitting over here is just that line of y is equal to x. So putting these two together in some way, some form, is going to give me this one function. That's it. So again, how we do piecewise functions is most of the time you'll see this funny little curly bracket that looks kind of like a sideways mustache, but you honestly see those brackets more in English. So after that, we just put, hey, I've got a sum function of x. So we're going to just call it f of x is equal to that curly bracket. And I know that I've got two different pieces. So I've got that negative x sitting there, and I've got that positive x. And then we've just got to limit the domains, because if it's both of these functions at once, it's obviously not going to be a function because it wouldn't pass that vertical line test. And we don't want that to go on. So how I'm going to say that is I'm just going to go, okay, where does this negative x take place? Well, that is from negative infinity, coming from the left all the way to where it stops, which is 0. And I'm going to go ahead and include 0 in that interval. I can include it in either 1. We just have to pick 1, because then it picks back up at 0, since I've already included 0 once in my interval. And then my green piece, which is that y equals x line, extends on and on and on and on forever, going to the right, which is just represented by infinity. Again, quick reminder, infinity is always a parenthesis, because we can never actually touch infinity. You can always get one more number than you think is the last number, which is why it receives a parenthesis and not a bracket. All right. Other quick note here is I could have had that negative x and positive x, f of x, blah, 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 equals. It is a lot more common to see inequalities here in piecewise functions than it is interval notation. So you guys will probably end up seeing something like x when x is less than 0, when it's negative x. Your x values actually have to be less than 0 for that particular function to be applied. And then f of x is x when it is 0 and larger. So that's just represented by x is greater than 0. Again, 0 is included. It is a filled in circle, just like this one should be. So one of these should have a line underneath it, just to say that 0 is indeed on that interval. Again, just pointing this out because these are a lot more common than interval notation when dealing with piecewise functions. All right, the last piecewise function that we're going to talk about is this bottom one. It says write a piecewise function for the graph on the right, which is great. It's cool. We should see right away that we have 3 different pieces. We've got this yellow piece here. We've got this green piece. And we've got, I'm just going to call it a blue piece. Alright, so the first thing I gotta do is decide what functions are represented by each of these little pieces. So I'm looking at this yellow piece and I'm like, okay, what function is that? Well, it's got up 1 over 2, so that's definitely 1/2 x. I wouldn't have to move this line up or down any, so that would just be plus 0. All right, this green piece would be down 2 over 1, so it's got a slope of -2. And then with that x, using that slope-intercept form, I do have to move it slightly up 2 because otherwise my particular point would be at 0, 0, so I actually had to move that entire line up 2. And then finally, this piece down here, it doesn't have any slope. That is a horizontal line. So all in all, keep forgetting my y equals and I don't mean to, or my f of x equals and I don't mean to. So finally, this particular line is going to be y equals -1, because that is that constant y value that is used over and over and over within that piece, which is why it's a y equals and not an x equals. So now it's time to go ahead, put this all together in that weird piecewise looking thing. So I definitely need that f of x equals, because I don't believe it's called anything else. So I've got f of x is equal to that weird curly bracket. I'm going to leave enough room to make 3 different lines on here. So I'm just going to go from left to right because that's how we read books. That's also how we read graphs. So I've got 1/2 x plus 0, or just 1/2 x. I've definitely got that -2x plus 2, and I've got that -1. The only thing I've got left to do is give my domains, and then I should be done with this problem. So this domain is from -2 to 0. So I got -2 and 0. They are both included on that particular domain. All right, my next little domain should be from 0 to 1. That's my x values that are covered. So my x is between 0 and 1. This time 0 is not included. That's why there's an open circle. Versus my 1 is included. So I should have that or equal to bar with my inequality. All right, and then finally, it is -1 from that +1 where we just left off, which is not included, all the way to, it looks like 3. And with that part, I'm done.